All right, what we're looking at right now is trying to investigate the angular acceleration of this disk as that weight applies a torque to it. But we're going to run into a couple of issues. Number one, there's not enough of a fall to allow us to have a full rotation. So we're going to have to only use small increments of angular displacement. And the other problem is we don't have a good alignment at the very beginning. In fact, if we move this thing to frame 0, or the very beginning, you can notice that we're not on the red line. In fact, we're just a sliver off the red line as far as the red dot's concerned. Our blue dot's in pretty good shape, but let's look at the red dot. Now, right now our angular velocity is 0. It's not moving. But as soon as we cut this string, or actually he's cutting the string, we're just hitting buttons, we notice that it starts to move. And it's going to be a lot of clicks later. Let me just click a little bit. In fact, I may just kind of fast forward right here. All right, now we're getting close. We want to mimic the way the dot looked before. I think that may just be a little too much. Yeah, I think so. Now, what we're trying to do is get the dot in the same alignment to that line as it was to the line previous. Now, what that means is it should represent a displacement of 2 pi divided by 12, or pi over 6. Now, that would be how much angular displacement had occurred. Now we could take the frames, which is 124 frames, and we could divide that by 240 frames per second to find out the amount of time. And with the time and the angular displacement, we can find out the average velocity. But note, that's the average velocity. It's not the actual velocity at that point, because remember, we started from 0 and we came to some new velocity, but an average velocity of whatever we come up with by dividing the angular displacement by the time. Now, we can actually figure out what the final velocity is here by using that average velocity equation. And when you start from 0, it's pretty easy. You just take the average and multiply it by 2. Now, to get another data point, we can use that number and we can actually keep going. And so we're going to go ahead and click, and it turns out it's not going to take that many clicks to get to the next point because we're already moving faster. So right about there, 174. So whatever that difference in frames divided by 240 would give us our time. And again, it's for the same angular displacement of pi over 6. Now with this information, having the idea of average velocity, we can figure out what that velocity is. So we have a velocity and a time, a velocity and a time, and a velocity and time. Let me point out which ones those are. We have 0 here, we have whatever the velocity is at this particular point, and we have whatever the velocity is at this point. That's basically 3 points. We could use those 3 points to make a graph, and a graph of velocity versus time, and that could allow us to find the slope, which is the acceleration, or we could use the kinematic equations and solve for what the angular acceleration had to be. Either method should work out to give us usable results, and that's how you'd go about trying to find the angular velocity in this case. I should say the angular acceleration with the angular velocities. So have fun.